Yeah, we'll be talking about post-quantum cryptography. So this is kind of an overview of like how we're going to go. So we're just going to kind of first like glaze over just what cryptography is. Then we'll go over a bit of what quantum computing is, and then we'll take a deeper look into these quantum algorithms, and then Dave will go like really deep into them, and then we'll finish out with Q&A. So just to begin, just to start off with like what cryptography is. So cryptography is like formally defined as, it's a method of storing and transmitting data in a particular form so that only those whom it's intended for can read and process it. So basically what this means is, in a nutshell, is cryptography like secures files and data. And this is like used throughout the world. Like it's used in ATMs, passwords, encrypting files, and as we know, it's used on the blockchain. And there's many different kinds of cryptographic protocols. So this includes, I'd say the three biggest ones were symmetric encryption, which is also known as secret key cryptography, asymmetric encryption, which is public key cryptography, and hash functions. So this is kind of an overview of how they work. So the first type, which is symmetric cryptography, is kind of like, so you have the plain text, which is the data that you want to encrypt, and you use a key to encrypt it into the ciphertext. And if you want to decrypt that information, you use that same key to decrypt the ciphertext back into the plain text. That's why it's called symmetric cryptography, because it's just one key. There's also the other one, which is asymmetric or public key encryption, which is the same except you use two different keys. You use one key to encrypt the plain text and use a different key to decrypt the ciphertext. And the third type of cryptographic protocol, which is pretty important, is a hash function. Now what a hash function does is it takes the plain text and it just converts it into a separate kind of ciphertext. It's meant to be a one-way irreversible function. And there's no like real key, because it's not meant, the ciphertext is not supposed to be invertible into the plain text. So the two we'll be focusing on one of the ones we'll be focusing on is public key cryptography. Now public key cryptography is usually used for authentication. So what this means is that if person A sends person B a message, person B needs to be able to open the message. And it's not necessary that they have to, in public key cryptography, the actual message is not as important, but it's that person B can actually open the message. And the way this works is, as I mentioned before, is it works with two keys. It's one that encrypts the message and one key that decrypts the message. And most of the work behind public key cryptography comes from what's called a trapdoor function. Now, a trapdoor function is basically a function that's easy to go one way, but difficult to go the other way. So what this means is, take, for example, 3 to the 5th power, which is 243. And it's easy to compute, given that you have 3 and 5. But if you're given 243, it's very hard to go from 243 and recover 3 and 5 as the numbers that make it up. And public key cryptography, like a pretty common example, and one that's used in blockchain a lot, is ECDSA. This is the elliptic curve digital signature algorithm, and it's a form of public key cryptography that's used pretty commonly in Bitcoin. Now, the other type of cryptographic protocol that we'll be focusing on are hash functions. So as I mentioned before, hash functions are a one-way function that converts from plain text into the ciphertext. And a hash function is used mostly to verify the integrity of the data. So what this means is that if you have some data that you want to hash, you take that data and you run it through the hash function, and you come out with the hash, or like the hash sum. And if you change the data even a little bit, then the hash of that data will completely change. So like an example of this is, you can see like the input here is Fox, and if you run the Fox through a hash function, you get this string. Now, if you change that Fox to the red fox runs across the ice and run through the same hash function, the string is completely different. Even if you make one minute change to the input, the hash function is supposed to work such that the hash of that input is completely different. And it makes it very easy to tell if the file has been tampered with or altered. And some common hash functions, especially the ones used in Bitcoin, are SHA-256 and RIPE-MD 160. So how exactly are these like cryptographic protocols actually used in blockchain? So I'm just going to quickly go over like some key aspects of Bitcoin. So Bitcoin has three main I guess values. These values would be the private key, a public key, and a Bitcoin address. So what the private key is, it's like kind of like you store all your Bitcoin in a Bitcoin wallet, and the private key is kind of like the password to that wallet. Like you need that private key to ensure basically that you own those funds. Your public key is like the username to the Bitcoin wallet, and your Bitcoin address is another value if you want to send someone else Bitcoin, you send it to that Bitcoin address and it'll get in your wallet. So how do these exactly work? So you start with a private key, which is just a random string, and with that private key, you run it through the elliptic curve cryptographic protocol to come up with the public key. And once you have that public key, you run the public key through two hash functions. You run it through both SHA and RIPE-MD160 in order to get your Bitcoin address. So as you can see, they're all linked together. To get the Bitcoin address, you need to have the private key from which you get the public key, from which you get that Bitcoin address. And they're all kind of secured through these cryptographic protocols. So it's meant to be that if you have the Bitcoin address, you can't reverse to get the public key. And in the same way, if you have the public key, you cannot reverse that to get the private key. So now after that, I'm just going to go touch a little bit into quantum computing. So what exactly is a quantum computer? So I'll first start with like what classical computing is. So in classical computing, everything is kind of encoded in bits, like basically zeros and ones. All data is stored with like lengths of zeros and ones. And to alter this data, you can put it through logic gates such as AND, ORs, or XORs. And if you want to change the data, you basically run it through those. And a bit in the computer is generally the smallest unit of information you'll have. Like at the base, everything will be stored in these bits. It's like a way this works is like assume that you have a number and it takes 64 bits to store. Now if you want to store like n of those numbers, it'll take 64 n bits to store inside the computer. Now quantum computing is similar, but instead of bits, it has these things called qubits. Now qubits have the same basic idea of storing information, but instead of storing like a 0 and a 1, it stores kind of like a proportion of 0 and 1. So a way to imagine this is imagine a sphere. Now in normal bits, the sphere can only take on the values of the North Pole and the South Pole, which are the 0 and 1. But a qubit can basically be any point on or inside the sphere. So it can be kind of a mix of the 0 and 1. And just as in classical computing, where you have logic gates like the AND, OR, XOR, in quantum computing, you have a quantum gate, which basically you can imagine as rotating the sphere in order to transform the qubit. And this whole process, the point on the sphere, like basically having a qubit having both the values of 0 and 1, this whole idea is called superposition. Going more into it, this kind of example is take a classical computer that's storing something in 3 bits. So if you have the number 111 in binary, that's a 7. That's true for any permutation of bits that you have. It can only refer to one value. But however, when you have qubits, like when you have superposition that comes into this, it allows for all representations. So imagine that you have 3 qubits. Now those 3 qubits, not only can it represent 111, but it can also represent all the 8 different combinations. Basically, these qubits can represent all the combinations of 3 bits. And basically, as the length of the qubits increase, then these combinations increase, and it turns out to be like 2 to like the length of the different values stored. So like if there were 10 qubits, you would have it could represent 2 to the 10 different representations.
Sorry, I feel kind of silly, but like. So we say a qubit is kind of like a sphere, but it can kind of take on, it says it has 2 values.
Mm-hmm.
It's a point on the sphere. It's a point on, it's a point on the
on the actual sphere.
Not inside the sphere, but
it could be also inside the sphere.
Yeah.
No, it has to be in the surface.
No, it could be a mixed state, so it's inside.
Well, you assume like you can think of it as, if we're dealing with one qubit at a time, you're in a probability distribution between the two states. The total probability has to be 1. So the idea of that's like you're on if you're dealing with 1 qubit, that means you're on the surface of a sphere. Because that means your probability has to be 1.
Okay. So what are the 2 values that we're talking about when we say there's a correlation of 2 values?
two-dimensional complex vector space. It's a modulus one, which defines the surface of the sphere. Because there's like, if you have a quantum state and you multiply by a complex number, that complex number is physically relevant.
It's a way to think of it as like a way to think of it as like a point on the sphere could represent like it does represent probability. So like it could be like you have an 80% chance of being a 1 or like a 20% chance of being a 0. And like I guess a way to visualize that is just like having the point on the sphere.
Got it.
If that makes sense.
Yeah, that does make sense.
Okay, and yeah.
So if you have 3 qubits which can represent all the permutations of 3 bits basically, then what information do I get out of this about these 3 bits?
So at the end when you measure, so in your circuit, like in your quantum algorithm, that is how the data, like that's what's represented there. But when you go to you can't actually see that probability distribution. When you go to measure, you're going to get a state, but the probability of you getting any particular state is the probability in that of that state in the distribution.
Is it a uniform probability?
So
yeah,
it's like
randomly getting one of the 9 states.
No, that depends on like the point of the sphere. So like each of like I think depending on the, correct me if I'm wrong, but like depending on like the qubits, like each of those like the 0001, 001, like they all have a separate probability of like I guess like when you actually read the qubits, they all have a separate probability of like being the one that's of being read.
Yeah, we assume it's a perfectly random system. The nature itself is random here. And the reason it's also a circle is because this is how the universe works. Probability, like the actual probability, is going to be the square of these values. So that gives you like your equation x squared plus y squared is 1, and your circle equation. So your actual values in your vector are like those aren't an actual probability. That squares your probability, which is why it gives a circle. I don't know if that confuses it more or makes it simpler.
Square of which values?
So if when you have a quantum bit, like you can think of it as like 50% probability of for state 1, 50% state 2. But like you can think of it this way, but the way it's actually represented is going to be the square root of these.
Okay.
So it'll be like 1 over the square root of 2, 1 over the square root of 2. So like when you square these and then add them together, you get 100%.
Okay.
That's just how the universe works.
I see.
I don't know a better way to explain it.
So that the norm of the vector is 1?
Yeah.
And in general, those are complex values.
Yeah.
Another pretty important aspect of quantum mechanics is entanglement. So entanglements, it's like basically the fact that qubits can be linked together. So what this means is that if you have 2 qubits that are linked together, if you change one of them, you can immediately, like the other one immediately changes based on that initial one. It doesn't matter how far apart the qubits are, as long as they're linked together, they can like a change in one reflects a change in the other. This is this principle is important to quantum mechanics, but it's not really as important to post-quantum cryptography. And that brings me to this. So there's a pretty common misconception. These 2 things are often kind of put into one pool. There's a difference between quantum cryptography and post-quantum cryptography. So quantum cryptography, it's also known as quantum key distribution. But basically what it is the main idea is that suppose you have a person, Alice, that wants to send Bob a message. And what quantum cryptography is it uses principles of quantum physics in order to send this message like with high enough security. And usually the point of quantum cryptography is that you can tell if someone is interfering with that, if someone is interfering with the message sending. And it's very easy to tell if the message is being tampered with. And once the message is sent across normally, then that key can be used the message that's sent across can be used as a key for other classical cryptographic protocols like a symmetric key or asymmetric. Basically what post-quantum cryptography is, it deals with something completely else. So it deals with like cryptographic protocols once quantum computing is more applicable. So like the RSA, the ECDSA, like what happens to these once quantum computing is out? And it kind of deals with like, how well do these fare against quantum cryptography, and what can be done about the protocols that are not quantum resistant, that can be broken by quantum computing. And I guess like a way to think of it, it's just like kind of the future of like modern cryptography as we know it.
Does that include like ZK snarks and that kind of thing?
That's more in classical computing.
Yeah.
There is work being done to make ZK snarks that are built on post-quantum cryptography primitives.
Yeah.
I don't know how far advanced they are yet.
So,
A big issue you run into is scalability, because we have a lot of primitives in post-quantum, but they're very expensive. Computationally expensive, I mean.
It's like I'm just going to kind of delve more into like the effect of quantum computing. So as I mentioned earlier, cryptographic protocols are all about security. And so like, when you have public key encryption, it relies on the fact that the public key cannot be used to find the private key. Otherwise anyone could, if you have the public key, anyone could just decrypt the message and find the private key. Same goes for hash functions. They're meant to be one way, and a hash function is considered broken if it can be reversed, if it can be inverted, or if you find a collision. What this means is like if you have two different inputs that map to the same output, then that would mean that the hash function is broken. As you can see, like what it would do is like it would basically make it so that if you have a Bitcoin address or a public key, you could use it to trace back to the private key, which I'll go more into a little later. So it's talking more about these actual algorithms. A pretty big algorithm is the RSA. So it's like a common security algorithm that's used like throughout the world, like in many different places. And it's very difficult with classical computing to break, because the main problem with breaking RSA is that you have to be able to factor a number n, which is the product of two different primes. So just to put this in perspective, RSA 768 was basically a kind of challenge that you have a 768-bit number, which I think is around like 240 digits long. And so it was factored, but it took processing power equal to about like 2,000 years on like a single core, like 2.2 gigahertz AMD processor. This is just on a 768-bit number, and if you increase that key size to like, over 2,000 bits, then this becomes like seemingly impossible with classical computers. Another one is SHA-256. So SHA-256 is a hash function that it takes in an input and it outputs a 256-bit number. The range of SHA-256 is 2 to the 256, meaning there's that many possible values that it could output to. Keep in mind, so let's say the current mining rate of the Bitcoin network is about it's like a pretty big number. You can see it's like 7 billion gigahashes per second, and so a common attack is called like a brute force attack, known as like a birthday attack. It's basically used in order to find a collision on these hash functions. And basically, if you use this mining rate and perform the birthday attack, in order to break SHA-256, it would take about like 194 billion years using that mining network if you perform birthday attack. So obviously, it's not very feasible to do with classical computing. So how does this change when you have quantum algorithms? Like how does quantum computing break classical cryptography? Now, quantum computing actually deals with algorithms. They're like limited by the classical computing, but as soon as you bring in quantum computers, like you can run all these algorithms. So most of these algorithms are based on two different algorithms, which are Shor's algorithm and Grover's algorithm. So Grover's algorithm was developed by Loeb Grover in 1996, and it's basically a quantum algorithm that can be applied to almost any function. So if you think about it, so let's say you have SHA-256. In like a brute force attack for SHA-256 to kind of invert it would be to run through if you have an output, to find the input, you could run through all the different inputs until you reach one that maps to the output. And in the worst case time, you'd have to run through all the different possibilities of SHA, which would be 2 to the 256. And what Grover's algorithm does is, instead of running through all n of the possibilities, you only have to run through a square root n of the possibilities. So to put this in perspective of SHA, for SHA-256, and in order to run through all the different inputs, you'd have to run through 2 to the 256 different inputs. With Grover's algorithm, you'd only have to run through 2 to the 128 different inputs. It's running through 2 to the 128 different inputs is still like pretty infeasible, but it's definitely an improvement over 2 to the 256. Does anyone have any questions so far about any of this? Okay, so Shor's algorithm is a little more applicable. So It was created by Peter Shor in 1994. And basically, Shor's algorithm is an algorithm that it solves the problem of factoring like large numbers. So within Shor's algorithm, there is a process called the QFT, or the quantum Fourier transform, which is a quantum algorithm that basically is used in Shor to facilitate the factoring of these numbers. And what this allows for it to happen is Shor's can be used to break the ECDSA, RSA, basically any form of asymmetric key cryptography. So just kind of revisiting Bitcoin transactions. In Bitcoin, like once quantum computing is out, a visible public key would be able to be reversed into a private key. So assume Bob sends Alice a certain amount of Bitcoin from his wallet. So as soon as he broadcasts that transaction, his public key is out and open to the world. So an attacker, or like a person with malicious intent, could basically use that public key and reverse it to find the private key. And once that happens, it takes time for that initial transaction to be confirmed. And once the hacker has the private key, they can do the same thing, and they can use Alice's Bitcoin and send it to someone else. And at that point, both the transactions have been broadcasted to the network, and they both have an even chance of actually going through, and only one of them will go through. So which means that Alice's transaction could just be it could just never happen, and instead her Bitcoin could be spent by a hacker.
Or you could give like a bigger mining fee and then take preference, right? And you would have a higher
Yeah,
chance.
exactly, yeah.
Okay, so if you're confused at any point, please stop me and ask a question. This is confusing stuff. So first, I want to talk a bit more Shor's algorithm, because this is what's breaking RSA and the discrete logarithm problem. So before we can talk about really post-quantum systems, you need to know what's going on here that's breaking our current systems. So then, a quick recap. So it can factor a n-bit number in polynomial time, which means RSA and Parity cryptography and such is broken. And it can also break the discrete log problem, which breaks digital signatures, elliptical curve digital signatures, and Diffie-Hellman and such. And so, how is the discrete? Yeah.
Speed log and what log?
Sorry, discrete logarithm problem. Yeah. Here's the equation for it, and right here. I'll get to it in a second.
Yeah.
But here's my question: how is factoring related to the discrete logarithm problem? Here's the discrete log problem. If you're given C, G, and P, how can you find X? If you can't read it, C is G to the power of X modulo P. This does not seem related to factoring at all. And in fact, there is no security reduction for the discrete log problem to factoring. Meaning that if you could solve factoring, this does not imply you have solved a discrete logarithm problem. So this means Shor's algorithm is doing something deeper. And so here's look at how it works. So we can roughly break it up into 3 steps. So at first, we're gonna have to figure out some function for our system that if we knew the period of this function, we could crack our original system. So at the end, I'll show you how RSA and the discrete log problem are both they're periodic functions which we want. Yeah.
Should I understand why finding the period of
I'm
function?
about to get to that.
Okay.
Yeah. So well, basically, the reason is if using some quantum circuitry, we can solve for the period. So if we can solve for the period, then we can go and solve. We've solved for the period. Then that means if that can break our original system, we've broken it.
The period just means, are we talking about the order, the cardinality?
Exactly.
Okay.
So yeah, if you know abstract algebra, it's some function which if we know if we know the order of something, that's what we're trying to break. Okay, so then we have to implement this function in a quantum circuit. This is actually the easier step because we have constructive theorems that tell us how to convert classical algorithms into quantum algorithms. If you're interested in this, look into reversible computing, because basically there's a fundamental property of quantum mechanics that it has to be reversible. And then step 3 is we solve for the period. So this is the part where this is the magic Shor's algorithm right here. To go into it fully, in depth, we need to have a full discussion of quantum circuits. To avoid that, I don't want to go into that, but I'll try to give an intuition of what's going on. So for quantum algorithms, you're operating on a probability distribution of what the qubits can be. So first, we normalize the probability distribution. We try to make all those probabilities the same for every possible state. Then we apply our periodic function. So it's going to it's going to operate on the whole possibility of those, it's going to operate on all the possible inputs. Then we're going to use something called the quantum Fourier transform. It's like the classical Fourier transform, but in quantum circuits. And so with that, once we measure it, we're going to get the period of the function. Once we do the quantum Fourier transform. So the two big speedups here is that we can first apply our function to the entire input space. And then the second speedup is the quantum Fourier transform is very fast compared to our classical one. Classically, the fast Fourier transform is n times 2 to the n. And the quantum Fourier transform is n squared, O n squared. So that's polynomial versus exponential time. It's a huge difference. You may have heard the fast Fourier transform is n log n. That's when n is the actual number we're talking about. Here we're talking about the number of bits. So now I'll try to show you why RSA and why RSA and the DLP, why we care about the period. So for RSA, the fundamental RSA equation is, if you can't read this, let me know. Does anyone have any questions so far? Okay, so the fundamental RSA equation is like our message to the power of E times D mod n is going to give us the message back. So this is basically the definition of a periodic function, and ED is the period here. Here, if you do symmetric algebra, it's order of the group. Yeah.
Sorry, the m on the left side and m on the right side are not the same.
They are the same. Sorry, do you mean these two m's?
Yeah.
They are the same. So this is our message, and we're RSA encrypting it. You encrypt m to the e and mod n. So this is the encryption, and to decrypt, you raise it to the d, which gives you m back. So this is why this is the definition of periodic function. So if we can get the period, we get ed. We've solved the system. So now for the discrete log problem, the equation is c is equal to some base point g to the power of a mod p. So now this on its own, the period of this doesn't tell us much. Due to abstract algebra, we know the period of this right here. Your g to the power of p, mod p is going to be g. You can intuit that by saying every time you multiply it, you're going to get a new element in there. And so after p elements, you're going to get back to where you started. So the period of this on its own doesn't tell us anything. So what we do is we construct a new function. Let me erase the top part. Let me use the marker. F of xy equal g to the x times c to the y in mod p. So this function that we just made right here has two periods. The first period is the same one we had here. Here, f of x plus p itself. But what I was just saying a second ago, this has a period of p, so this is still going to have the period of p, but it has a second period. So if we raise x, so if we would say x is going to equal x plus a, that's going to mean we're essentially multiplying by c again. And then if we decrease y by 1, then we just also divided by c. So we've removed a factor of c. So that gives us the same number again. Does that make sense? Okay. Okay. So now, I'll write it down first. So if we increase x in this equation by a, then that's the same as by this identity right here. That's the same as multiplying by c. But then if we decrease y by 1, that's the same as removing a factor of c. So that means we're going to get the same exact value again. So that's going to equal f of x, y. But the thing is, this is a period right here. So if we know with the quantum Fourier transform, we can solve for this period. And so then with this A is what we're looking for, which is part of the period. So we can then solve the discrete log problem with Shor's algorithm. So Shor's algorithm solves the period of these. So that's why like the discrete log problem and RSA gets broken by Shor's algorithm. Then here's a few like technical points. The technical term for what Shor's algorithm solves is it's the hidden subgroup problem on abelian groups. If you know a bit of if you know a lot of abstract algebra, that'll probably mean a lot. Basically, it's finding the period, and with one caveat, you have to have the property that it's abelian or commutative. AB has to equal BA. Okay. So then there are actually some quantum algorithms. This typo right there. That can factor fast on Shor's algorithm. The ones it's called GEECM. You can look into it later if you want. Here's the number of qubits you need to factor RSA modulus of 2048 bits. You need about 4,100 qubits, assuming there's no errors. So the big issue with constructing quantum algorithms is that in like putting into practice, you need extra qubits to handle errors because we can't construct these things perfectly. So the largest quantum computer that I know of is one Google started working on last year, which is 47 qubits. So it's and we're getting more and more qubits as time's progressing. So if we assume that the growth is going to be like how it has been, we have to start worrying about this stuff now. Then elliptical curves can be broken even sooner. Up to 1,500 qubits. And I list this curve specifically because this is what's used in SSL right now. It's what's used in Monero. It's the common curve everyone's using. Does anyone have any questions at this point? Yeah.
So this means that for a given number of actual bits of security, RSA is more resistant against quantum computers because you need more qubits.
Yes.
To break the same level of like actual bits of security because it uses giant numbers.
Yes, I think so. I don't know exactly how many bits of security 2048-bit moduli give you. If it's around one, I think elliptical curves. This curve specifically gives you about 128 bits. I'm pretty sure 2048 gives you around 128. I could be wrong on that. But in general, well, I think RSA scale, you need more qubits as the moduli gets bigger than you do for elliptical curves. Then, so now I'll talk about are there any more questions? I know that was a lot, and it's...
I guess I have one.
Yeah.
About like physical quantum computers. So when we talk about like how many qubits it has.
Yes.
Like in a classical computer, you have like a 32-bit computer or a 64-bit computer, and that's like the instruction size and the word size and all of that.
Yeah.
And basically, like if you wanted to make, a 1024-bit computer chip, you would have to increase everything by a huge amount. Like all of the buses would get bigger, all of the stuff that I don't actually know about. Like all of that would get a lot more complicated. So to actually build a 1,500 qubit computer, you would have to physically build like 1,500 parallel things for every aspect of the computer, right?
So the difference is for like our normal computers, we want it to do a lot of things.
Right.
For these quantum computers, we just want it to be just run the specific algorithm.
Right.
So
you wouldn't build a general purpose CPU, I guess.
Yeah. So like, I know that I've never explained this diagram, but here's a couple here are some some circuit components we just put these circuit components in like sequence on the quantum bits.
Build an ASIC.
Yeah.
That have like 1,500 input lines.
I mean, you'd have like you have some lattice of qubits, and you can do certain sets of gates on pairs of them, but you can do different algorithms as long as you can express them as like doing certain gates on certain pairs of qubits.
Okay, so the engineering problem wouldn't be like it's obviously very hard, but it wouldn't be the same kind of like problem of trying to build like a 1,500-bit classical computer.
I mean, in some sense, like a quantum computer has like a word length of 2, and that you act on 2 qubits at a time.
Right.
Maybe in parallel, maybe you act on like disjoint pairs of qubits, but
okay. So it's a different engineering problem that's obviously very hard, but it's not the same kind of
I think a lot of it's, correct me if I'm wrong, but I think a lot of the problem in building quantum computers is stability.
Right.
So like you have to make sure the quantum bits don't interact with each other.
Right.
And there's a host
They
of
do.
quantum physics problems that I'm sure are very hard and I don't know much about,
Okay.
but you have to like solve there.
Right.
Yeah, so I guess to build on that point, it's like the architecture of a quantum computer is completely different
Right.
than,
Mhm.
than the architecture of that.
Yeah, we're not trying to make a quantum computer do anything. We're not trying to make our instance of it do anything.
Right.
We're trying to make it run this one algorithm. And I forgot, there's one key point I forgot to hit on earlier. So when you're having these circuits, you actually have to adjust the components of the circuit based on the public key you're trying to break.
Okay. Right. So it'd be a computer you build to break one key.
There may be ways to make it more general purpose.
Right.
I don't
That's a
know.
whole other
Yeah.
engineering problem then.
20
Like a-
years from now,
interesting.
yeah.
Like a quantum FPGA.
No, you wouldn't make a computer to break one key. You build a computer
To run one
intended
algorithm.
to break one type of crypto system.
Okay.
But they're not that limited.
Okay. So then here, I'll talk about some like hard problems in that we try to base our post-quantum systems on, which these problems we have no known quantum algorithm to make them easier.
Oh,
So-
question.
Yeah,
Do we have is it just the case that we don't know a quantum algorithm that makes them easier, that we have some sort of formal or informal notion that there is no quantum algorithm?
so I think it's some of both. There's no proof that there's no quantum algorithm that can do it faster. I don't know if it's even possible to prove. But we have a general notion that we think it should be secure against quantum algorithms because the type of problems they are. So this first one's called the shortest vector problem. So we have some lattice. A lattice is basically like a vector space which has integer components. So like we have two basis vectors, and then they're spanning the entire space, but only integer multiples. So like here's base vector like times 1, times 2, times 3, times 1.5 is not in the space, not in our lattice. So the shortest vector problem is saying that we want to find the smallest possible vector in our lattice. And so in this diagram I have right here, the shortest vector is from here to here, or here. Like that's a solution of the system. Now this becomes very hard as like you increase the number of dimensions, and you make these all your basis vectors pretty parallel. Like not exactly parallel, but like close together. Because you can't just shift the basis around. And so you also get another thing. There's something you can do to make this even harder. So you can change what you mean by distance. There are a couple of like different math equations you have to follow in order to make it sensible. But there's still alternate definitions of distance you can use. Then there's another very similar problem called the closest vector problem. So it says that we pick some point in space, and we want to find the vector that's closest to that point. If we can solve the closest vector problem, we can also solve the shortest vector problem. So the closest vector problem can be thought of as a slightly harder variant of the shortest vector. Does this make sense?
What's the difference between the closest vector and the shortest vector?
Okay, so the shortest vector is we want to find the vector that's the smallest in the entire space.
Just closest to 0.
Yeah, close to 0. And then the closest vector is we pick some arbitrary point. I could have picked a point right here, and we want to find the vector that's closest to that, whose distance from the point is minimized. And so,
It's not really clear to me why those things are hard. Like the shortest vector is just equal to 0.
oh, sorry, that's called the trivial solution. You want the one that's not 0. I should have specified that.
So interesting. And you can't just like set. Okay, I can see how
So,
that's difficult.
Like, see, normally, if our basis is orthogonal, it's pretty easy. But the more and more parallel these get, and the more and more dimensions we add, the harder it gets.
So what is an instance of this problem? Just like a specification of the lattice and the distance metric?
Yes, for the shortest vector. And the closest vector is you also add a point, the point you want.
And everything's integer?
Yes. I think that sometimes people do it over not the integers, like they do over the complex plane. I don't know if that's what's used in our current systems or not, though.
What's the classical runtime for?
So the algorithm's Lenstra reduction that we use to solve this And basically it means that we're trying to find a way to remove some basis vectors. I don't remember the runtime off the top of my head. Sorry. Yeah, we can probably Google it later. Lenstra reduction.
What are the hard case results are there for this?
Sorry, what do you mean?
Is it NP hard for certain?
Yes, they are NP hard.
Okay.
So the couple reasons we like lattice problems. So for a lot of our current, like, let's say, for an average case lattice problem that you can give, it's going to be very hard to solve. We have a provable security for this. So for a lot of NP problems, it's not true. We only have provable security for the worst case. If I give you like a random number, there's a 50% probability that it's going to be divisible by 2. 33% probability it's going to be divisible by 3. So on the average case, it's not terribly hard. Then there's no quantum algorithms that can solve it faster than the classical, which is a very nice thing. And then there are several routes to make it harder, or increase the dimension of the lattice, make those bases more and more more and more parallel, less orthogonal to each other, and change the distance metric. And then there's one thing I want to say. Lattices have a nice algebraic structure, which means that you can make a lot of systems on them. You can do signatures. There's encryptions. We think we can do blind signatures. With enough work. One crypto system we have that uses these lattice problems is NTRU. It uses the shortest vector problem. NIST has recommended this algorithm for further cryptanalysis and then potentially standardization later. NIST being like our government agency who does a lot of this stuff, who analyzes all of this. And they have an encryption scheme and a signature scheme. Their first signature scheme was broken. They have since made a second one, in which has a very small signature size. So I know I say so, 1 kilobyte size is small, which it's kind of huge when you compare it to elliptical curves. Because elliptical curves, the signatures we use in Bitcoin are around 73 bits, if I'm remembering correctly. So a kilobyte's a huge difference. But in the post-quantum systems, this is pretty small. So then we have another set of problems called learning with errors. This comes from machine learning, and so the nice thing about these is the easiest way to solve these is the worst case lattice problems from before, and so the problem you're given is if you have a set of inputs and the set of inputs can be like arbitrarily big for any vector. We're talking about vectors, so you can have a vector of like 10 inputs and then 1 output, and you want to you're sure that there is some function that maps all those inputs to the output, and this function is linear, but it has a noise model. So there are errors, which is learning with errors, but you get to know the noise model. So the problem is find this function, and so one scheme is Bliss. I think this was code-developed by some Google engineers along with other cryptographers. The signature size is 5 kilobytes. Kilobits. 5 kilobits for, what's it called? 128 bits of security, which is what we have in the elliptical curve 25519. So again, a huge size difference. But for Bliss, NIST has also recommended this for further study and then standardization.
So what sort of noise? I mean, this is just like solving a set of linear equations. Right?
Yeah, but then you have add noise into it. So for your outputs, it's not going to match perfectly. You're going to have it could be a uniform noise in some range,
Okay.
or you get to choose a noise model. The algorithms for solving it are essentially solving those previous problems for lattices.
Right.
And then the next system, this one actually these are all very math heavy. Like the math you need gets very complicated very fast. The next one is called supersingular isogeny Diffie-Hellman. So the nice thing is the title itself is very complicated because it is complicated inside, but it can act a lot like Diffie-Hellman. So it supports perfect forward secrecy, meaning that if I go to a website and then we get a shared key, we can encrypt our data. But then assuming they don't store everything on their side, Right? If the government cracks their public key, they can't figure out our old communications. Our old communications were still secure even if the government had or anyone had them stored, which is a very nice thing. And the public keys for this are small relative to other post-quantum systems. The math is insanely complicated. And then we have another set of cryptography things like Merkle. They're called Lamport signatures or Merkle signatures. So basically, they're provably secure if our hash function is secure, but they take up a lot of space. Yes, I believe Merkle signatures tend to be around 8 kilobytes. Again, huge compared to our 73 bytes for elliptical curves. So the nice thing is we do know these are secure if the hash functions themselves are secure. And these might be able to be implemented efficiently for cryptocurrencies because we already are using hashes for proof of work. So then, to wrap up, what can cryptocurrencies do now, like in the face of in the face of quantum computers coming in the near future? So they can adopt a post-quantum signature scheme, though this adds scalability costs. We're already having concerns that we're not getting enough transactions per unit time, and if we use a post-quantum signature, the signature sizes are going to grow a lot, and then they're going to only get harder to compute. I believe the signatures take significantly longer for these post-quantum systems than they do on the classical systems. And then we also have another issue that quantum computers could then drive up the amount of complexity you need for proof of work, because due to Grover's algorithm, you can solve in essentially square root n time. So if we assume that we can build quantum computers of similar strength to what we can do in classically, then we'd have to square the proof of work complexity to get the same level of security. And then not everyone could then afford quantum computers, which promotes centralization. Though this issue is still present in Bitcoin mining because mining pools.
Okay, so just to wrap up, it's like quantum computing is coming sometime in the near future. Who knows when it could be? Could be in the next 10 years. Could be, but it is coming soon, and it will break a lot of classical cryptography as we know it today. But there are solutions to this, and blockchain still does have a pretty good future post quantum. There's some quantum resistant ledgers, and we actually have a professor here who's going to talk about one of his platforms that are quantum resistant. And that concludes our presentations. Does anyone have any questions?
Can we go over that diagram one more time? Not those equations over there.
Oh yeah, sure. Okay.
Can we give them names for private keys and public keys and if that's applicable?
Yeah, sure. So do you want to go RSA or just the discrete log problem?
DLP.
Okay. So for DLP, this is the discrete log problem is you build the public key and private key stuff on top of the discrete log problem. So for the discrete log problem, this right here is a secret. Where's the blue marker? It's kind of dead. Here it is. This value of A right here is the secret. So this modulus P, I never said it, but it can really be anything. It's just you have greater security when it's a prime. If it's not a prime, then you can make it way faster by factoring it, which we already showed factoring is feasible. So it makes sense to assume it's a prime. And then G is just some base point. We have to agree on this base point. And then C is essentially the result of this. It's often what you're giving out publicly, because you can assume that they can't figure out A. Okay, so I can list the Diffie-Hellman scheme, which is eventually how you use this a lot of the time. So you have big A equals G to the little a mod P. Can you read this?
Yeah.
Okay, cool. Then B equals G to the B mod P. So in Diffie-Hellman, both parties exchange big A and big B. So then any interceptor only knows these two. But then internally, they compute their shared key. I'll call it K. Is going to equal. So for person A, that's going to equal the other person's number. So big B to little a, because person A gets to know little a. We assume no one else does because they can't break the discrete log problem. So then this, because this ends up being G to the B to the A. Do the property of exponents becomes G to the AB. Then person B computes basically the same thing. They do big A to the little b, mod P. And you get the same thing. So that's why there isn't really a public key in the setting. C is a public value, the discrete log problem, and A is a secret. So now we can with Shor's algorithm, we can solve for the period of a function. So we construct this function right here.
That would be just like say we're gonna have this new function.
Yeah.
We're gonna reframe this problem in terms of C.
Yeah, exactly. And so now, this is how we can make with this new function. If we know the periods of this function, then we can break the discrete log problem. And then we say that we can solve for the periods with the quantum Fourier transform.
Okay, then I think that concludes our presentation. And
my name is Rustam Islamov. I'm from Russia. I'm professor at Moscow University of Physics and Technology. I graduated at two universities. I'm Doctor of Nuclear Engineering and I'm PhD in Mathematics. And here with my business partner, we set up a company who is working in PostQuantum encryption and developing many interesting things. And now chairman of the company is Ambassador Gilbert Robinson. Our general counsel is former director of FBI FCA. Forget about this. So nevertheless, Rupert Allen, he graduated Berkeley. And he insisted on me coming and give our first presentation here. That is first public presentation of the very new invention, which was pending a patent in July 30 this year. So you are the first audience who will be able to listen to this. So please be polite. Okay, so let's go to paradigm of asymmetric encryption key exchange, which we hear today. Thank you very much. It was very correct. So based on complexity, what it means, the task of decryption by hacker has an exact solution. Remember that there's always precise solution. Hacker should find this goal. Second, the difficulty of decryption task depends on the key size. Oh, complexity, something like this. In partial case, on key size. And the longer the key, the more secure the cryptography. Second, deterministic representation. The key appears the same in repeated network transactions. Predictable. From many point of view, it's not secure. End result, the endless struggle between the sword and the shield. The best hardware wins. We're talking about hardware. And quantum computer wins easily classic computer. So we have endless competition. Longer key, we have more powerful computer, classical computer. Now we say, okay, we can develop longer key. But longer key takes more time to operate. And finally, we still have slow time to protect, to develop protection, and so on. What about new paradigm? What we develop? We develop polynomial white noise key exchange paradigm. First of all, it's based on so-called underdeterminate systems. It's not complexity. It means that task of decryption by hacker does not have an exact solution. Second, the difficulty of decryption doesn't depend on the key size, and cryptography is secure regardless of the key length. I'll show why. And stochastic representation. The key appears differently during repeated network transactions, random. It means that you cannot predict what kind of information is going in. Result, the software solution security does not depend on hardware power at all, no matter what you use. Memory stick, mobile phone, laptop, or quantum computer. They will absolutely equal in terms of security. And the method of equally secure against both ordinary and quantum computing. Now, I'll just explain you in terms of metaphor. I want to give you a key. on a public network using public-private computing. Of course, it's very easy to see private key, public key, calculate. Now look, I put this deterministic my key and send to you, but I put it inside random envelope. Random envelope using undetermined system, which nobody can decrypt, only me. And I send it to you. And everybody see only random envelope. Every time it's random, every time it's different. What you can do? Nothing. Because there's only person, it's me, who can open this. What you do? You put my envelope inside your random envelope and send it to me back. In terms of physics, it's impossible to take out inside envelope, not breaking the outside envelope. But in mathematics, and that is invention of function, it's possible that I take my secret envelope out and return back to you your random envelope with my key, and you open it. You and only you, nobody else. That is how it works, and now that is an example of two different paradigms. RSA protocol, elliptic curves, they have solution in this area. Can you resolve this problem? More complex, less complex, more secure, less secure, but it has precise solution. When you go to undetermined system, what we use, can you resolve the system? How? That is prime numbers. It's definitely 711. At least one time in your year, in your life, you know what it is, 711. Here, real numbers. That is infinite possible solution. And the problem is that here you definitely know that solution exists. In this case, you definitely know that even if you go through the precise what I wanted to set the key, you cannot prove that is my key. And you cannot check it. So now this idea, and now how it was implemented. So first of all, several definitions. Key matrix, what we used to use as a set of integer numbers. That is a key, usually. Like set of bits or bytes. First of all, we transform in a real number matrices. Later, I'll show you how it can be done easily. And just for simplicity, let's say just one matrix. Just one matrix. Let's consider that is a set of key. It's this matrix is set of key. It's very easy. That is integer number. That is real numbers. I'll show you how to transform it. And then that is the key first random envelope from Alice to Bob. Bob put his random envelope, and then I get rid of my random envelope and send to Bob. Bob, get the key. Let's go from this scheme slowly. Alice has matrix X as a key. She generates random matrix Y and center symmetric matrix A and B.
Sorry, what does that mean? Center symmetric.
Later I'll explain. Or we can start from the beginning. Matrix picture, that is inverse matrix. Are you familiar with linear algebra? Everybody? Who never hear about this? Everybody? Never hear about it? I'm just kidding. That is determinant. Okay. Identity matrix is 1. You multiply inverse matrix to matrix is equal to 1. Center symmetric matrix when diagonal elements similar, and it has very nice feature. It always, you can change the place. Always. That's very nice feature. Later I'll show you how we use it. And singular matrix. It's very important. Singular matrix doesn't allow you to resolve the system of equations. Singular matrix brings us undetermined systems. Like equation. If singular matrix X and you have this equation, B is also singular, no matter what kind of A is. And in this case, if you know B and singular matrix A, you can calculate matrix X. But if you know B and X, you never can calculate matrix E. Even this equation is so simple. Then we'll use this feature later. So what Alice do? Alice generate matrix Y, regular matrix, and two center symmetric matrix A and B, and multiply it to these matrices, mixing with the key. And this white noise, because these random matrices consist of uniform distributed numbers, and there is polynomial white noise, which is not informative at all. Just combination of random values, all of them distributed, uniform distribution on a period from 1 to 2. Both get these matrices M1 and M2 and send random matrices DH and C back in this way. Let's show first pass. Alice creates the key as a singular matrix. Then matrix Y, an inverse matrix, and central symmetric matrix. That's it. Nothing difficult. Very simple. You multiply matrices 2 by 2. It's so simple. And then Alice just sent them to Bob. What Bob does, he generates random matrix DH and central symmetric matrix C, and multiply C from left, inverse matrix from right, DH close to envelope. Both matrices he covers with his envelope and send it back. So Alice receives matrix from. What Alice does? First of all, she take off her envelope, multiplying to matrix, inverse matrix A and B. Do you see this? We can change them because they're center symmetric. And we change this, and after that, we can get rid of them. This and this. Now look at this. We use specially the random matrix C, inverse matrix, and C here, and then we multiply both of them, like this one. You see, there is no any Alice envelope anymore, because D and H matrix belong to Bob. And Bob gets his matrices back and just get rid of them, and gets precise the key. That's it. So easy, so primitive. Now look, what is resistant of this encryption? Every time we send matrices through a network, we see how many unknown by the third party variables we have. 11 first time, and we see 8 visible numbers. These systems are determined. It's like x plus y is equal to 77. You can resolve it. Any kind of x may satisfy these equations. Second pass, Bob, also 10 and 8, because we use matrices. But we use in such an artificial way that we use matrix here and here, the same matrix, in 2 flows, so that when we multiply, they disappear. And finally, Alice gets this, nothing new, but even these additional 4 numbers, still less than we need. This system is absolutely resistant from the third party, like from hacking. What you can see only white noise in the network. Later I will show you this example. What is the problem with this? Can this somehow decrypted by matrices? For example, matrix X, just formally, can be represented by a visible matrix like this. The problem is that matrix M4, M5, and M2 is also singular. They don't have inverse matrix. It's division by 0. You cannot get rid of them because that is a log of singular matrix. The same here. You cannot get even this multiplication of matrix just to calculate something. Nothing is available. You don't have choice. Man in the middle attack. Unfortunately, if Alice never knows Bob, Mallory can steal their key. Because it's computer, it's network, it's anonymous. You never know, is it Bob or is it Mallory? There is no any evidence. To protect against man-in-the-middle attack, we just add authentication transaction. We add a third party who knows both Alice and Bob. Just know them. Look like Alice agreed with Ed and said there special matrix NA, like authentication matrix. And Bob also put the Ed this matrix NA, NB, and Ed just keep it. So the difference between first algorithm and the second one is only that we add additional matrix G, which goes two ways. First directly to Bob, and third indirectly through the Ed. Ed does only one thing. He multiplies with this matrix NE, which keep in memory. And mechanism similar, just a little bit longer. In this case, Mallory, man in the middle attack, he can do nothing, absolutely nothing. And now, you see that that is resistant against man in the middle attack. Mallory always have to resolve the system, which he sees 20 variables, but he needs to find 23 to get the key. That's just a big example. It's real software. Just example the key. That is what we see in the network. And that's the key. If you look at this, all operation takes maybe 20 operators for each matrix. Fast, easily, and you don't need to calculate prime numbers, B prime numbers. You can take any key, even equal to 4. And also resistant. Polynomial white noise. We censor into that 20,000 times, number 65, like letter A, ASC code. And that is distribution functions for all variables that is seen by the third party. No parameters, nothing. That is polynomial white noise. That's it. No information, nothing. Okay, now we can put server here with matrices, transaction matrices, and clients. All clients have their so-called authentication number, which dedicate to other client. Everybody can exchange the key using central server, and server has only not personal matrix of client, but combination of these matrices. And result is that even server is compromised and third party can see all these matrices, the system is still secure. Still secure. It means that you can set up a blockchain of this publicly, an organized society of clients who can exchange the key between each other and have messengers, emails, I don't know, maybe hedge fund, exchange information secure against quantum computer. Forget about prime numbers, factorization, elliptic curves. I had a coffee with Tahir who developed elliptic curves. We were talking and he was almost crying. He said, I spent 10 years for standardization. And now, NSA published an official site that please don't, companies will appreciate who changed it from RSA protocol to elliptic curves, but please don't do this because quantum computers are coming, it makes no sense. So that is first algorithm that we invented. That is patent, you see this, July 30. Another algorithm dedicates to authentication system. When I didn't put here because it takes too long time, too much information for the first time. And third algorithm we are still thinking about this, it's about how to make electronic signature. I'm not sure that we need this. In this case, maybe we can develop different, maybe, paradigm of blockchain. Maybe you don't need, I didn't work on this yet. Because that is why I'm here, that we are seeking, looking for talented guys who can be join our team and who will develop something new. That's why I'm giving a presentation today. So thank you very much. Should you have any questions? Any complaints, threats? Welcome.
All matrices are 2 by 2.
Right?
All matrices are 2 by 2.
Yes. But you can extend the key, you know, it doesn't matter. If you need long key, you can make sets of 2 by 2. Because if you go to the feature, central symmetric matrix. If you take matrix 3 by 3, you'll find that there will be diagonal A1, all other elements will be A2. And the algorithm will not work.
So X is random, right?
Right?
X is random?
No. X is, okay, let me, right.
X is the key, right?
Yeah. For example, you develop a key. Set of signals. Like your key is like quotes. Like string. You generate random from 1 to 2 random number. For example, the first random number is 0.278913. And second is 0, 12. You take this number and put to this position. You take this number and put to this position. Because for even 32 bits computer, after 20 calculations, 5 numbers guarantee of precision after calculation. And here, with these 5 numbers, and of course for a 64-bit processor, it will take. So we can put this number here, that's it. No matter what kind of key you have, you always put it inside this random. set and send as a white noise. And because this white noise, even if these numbers will be deterministic, due to these calculations, it becomes like without parameters.
Why embed them in random numbers in the first place?
Right?
Why like embed the thing you want to send in random numbers in the first place if that's not necessary?
I'll tell you, it's necessary to be all these numbers within this.
So what do you mean by that between 1 and 2? All those numbers are between 0 and 1.
Because you have inverse function.
What?
You have inverse function. Okay. Do you see this inverse function?
Yeah.
Okay. It comes from accuracy theory or precision theory. You should divide x1, x4 minus x2, x3. If x guarantees between 2 and 3, and this one will guarantee between 1 and 2, or 0 and 1. It's like maximum will be 3, minimum will be 4 minus 9 and 4.
Right, okay. So you want
So
it to be
that-
0.
Yes, so that you never divide to 0. You divide only maximum 9, minimum 4. And when you divide to such number, all your calculations still remain very precise. Very precise. That is why you just control where you put your numbers. The only technical problem. All other, extremely precise. You know, I have a tester, computer scientist, who was testing this method. He was the most terrible tester. So ugly, so terrible, so impolite. He special tested all numbers from 0 to 1 to, or from 2 to 3 to all numbers like several weeks to check whether it's stable. This terrible tester is my middle son, Dennis. You know that he's never respect parents, never. He graduated university and he kept saying, "Oh, father, that's a mistake in the algorithm." Check your software. No, you are guilty. That is your mistaken algorithm. And finally, he checked everything. And now it's proven that it's stable based on not only theoretical but practical calculations. So that's briefly what I wanted to tell you today, and thank you very much for being patient. Should you have more questions? By the way, please read this. Oh, I didn't. Rupert. Email Croc's ear and his name Rupert. Okay, just send him a mail because he speaks English, he is great at Berkeley. He'll communicate with you much more, maybe comfortable for you.
Question.
Oh, okay,
How can this be standardized if there's an outstanding patent on it?
great. That is a great question because we already had meetings with people from NSA. You know what NSA is? Yes.
Not personally.
So I personally had a meeting with them. So, and I talked to Bill Crowell, a former deputy director of NSA. I also talked to Andrew Gold, who is general counsel of former CIA in Washington, D.C. There are two different processes. You should know this. The first process is technology process. Like quantum computers, somebody developed them, maybe in Germany, maybe in Australia, maybe in China, in Japan, everybody developed them. Second process is bureaucratic process. Like NSA said, we have a problem. What is quantum security? What do you do? Oh, we have a program for the next 5 years. And in 5 years, NIST, do you know NIST? Will develop what? A guideline. What? A guideline what we plan to do with security against quantum computers. So standardization of any process takes, as you remember, elliptic curves, the hero was crying when we drank coffee. He said, 10 years, and now? I said, sorry. I asked him, here I said, would like to be our tester. He said, no, I cannot, because psychology can understand him. Then I come saying, oh, you spent 10 years for nothing else. Now everybody say, oh, elliptic curves, RSA. I talked to Edison, by the way, 2 years ago on the conference RSA. There was presentation, blockchain is dead, or Bitcoin is dead, or maybe alive. It was in San Francisco. I came to him and said, listen, Adi, what do you think about post-quantum encryption? And he said, Rustam, if you want to talk about this, you'd better come to me in 50 years. It was 2 years ago. I said, oh, really? Adi, you're a professor of mathematics in Israel? He said, yes. I'm a professor of mathematics in Russia, in Moscow. What is your plan for next summer holidays? He said, oh, you know, Rustam, it's so uncertain. I said, I'm sorry, fuck Adam. You don't know what you do next year? And you want to convince me that computer will appear in 50 years? He said, oh, I'm sorry, okay. Maybe in 30 years. Then he looked at me and said, by the way, should you have any ideas? I'm ready to listen to you. I said, for sure I have some ideas. I'll share with you. He said, when? I said, in 50 years. So that is always a bureaucratic system and technology. What I can tell you, if we start right now, today, substitute this for key exchange process and build systems, we're already late. Because now to change all credit cards, to change all mobile phone systems, or transactions between banks, it'll take up to 20 years. That's not my opinion, that's expert opinion. But quantum computer, do we have at least 20 years? Who can prove me? It may happen. So what we do now, we develop right now the system. We just started to develop the system and we talk to people. NSA, we try to be very correct because NSA has to give us some comments, because you know there's expert control. That the key, his lands, more than 256, cannot be sold abroad. You know this. That is limitation. In our case, we don't have any key. We don't have any limitation. The key can be whatever you want. So, and we got very nice comments from NSA. We asked, can we commercialize it? And they said that's very beautiful paper. The best paper I ever got in my work in nuclear safety and security in my life. No comments. That's now free, and we're free to do this. What we do now, next step for cryptocurrency. We will develop ecosystem. We'll develop maybe hedge fund, maybe trading platforms for users, for people. So the faster we involve in a not standardized area, like not for government. Actually, we plan this month to go to Washington, D.C. again because our chairman of our company, Crocs.io, you know, his ambassador, Gilbert Robbins, former assistant to President Reagan, you know. And he said, oh, Rustam, let's talk to Senator this like this. He's chairman of some science and technology committee, all this. I said, Gil, I can talk to everybody, you know. The problem is that is a bureaucratic system, and we cannot wait. We'd better go to private sector, to business sector, rather than wait when government decided. Because the problem in the bureaucratic system, because I used to work with Sandia National Labs, Brookhaven National Labs in more than 35 years in nuclear safety and security, probabilistic risk analysis, and Nuclear Regulatory Commission of the United States, Department of Energy, and Department of Defense, in IAEA, International Agency of Atomic Energy. I was expert in anti-terrorist attack and so-called guidelines for physical protection and information protection. And I know quite well how governmental system works. Maybe too well, because I was one of the author of some governmental documents and international documents. So it's very long process. And the problem is that in private market, if you do something, you take risk on your own. You get more money if you're successful, but you get nothing, no support if you're not successful. In government system, you are protected from the bureaucratic system. But at the same time, people don't have any motivation to do anything. Because no matter what they do, they still have salary. That's it. So it's very difficult to talk.